All right, so today we are starting chapter 6, and chapters 6, 7, and 8 mark pretty much what we're going to be doing for the trig part of the class. So first thing before I even start the section, I usually just put the word up, take a look at it, and see if there's any part of that word, either the beginning, the end, or something that we recognize. So putting the word trigonometry up, is there any part of that word that people recognize? Maybe they've seen it in another word or subject or something. Yep.
It starts with try, which
Okay.
is 3.
So yeah, try has to do with 3, like tricycle, 3 wheels, triangle, 3 sides. So try means 3. Yep. Any other part of that word? Yeah.
Meter, measuring.
Yeah. Which part of that word do you see that means measuring? Metri, yeah. So measuring or measurement. And we see the word metri in various subjects end with that, like trigonometry, geometry. I guess that's it. But anyway, there's a couple. So metri means measurement. And there's one more part of that word that...
It's the gone.
The gone, yeah. What does gone mean?
Shape.
Yeah, I mean, specifically, it's
Yeah.
something about the shape. Yep.
Like above a certain
The angle.
amount of size or something.
Okay.
Sides, yeah. It has to do with sides. So, like, every shape has a name that ends in gon, like for polygons. We don't always use that name. For a 3-sided polygon, we usually call it a triangle, but you can call it a trigon. 5-sided shape, pentagon, 6-sided, hexagon, 8-sided, octagon. Those are pretty common. 4-sided, we normally call it quadrilateral, but you can also call it a something ending in gon, not quadragon. That's not the name. Anybody know another prefix that means 4 besides quad? Yep.
Tetra.
Yeah, exactly. Tetragon is the 4-sided shape, and that's where the name Tetris comes from, because each shape in Tetris is 4 blocks. So that's why I call it Tetris. So the idea of this is we're measuring a shape with 3 sides. And we're using the measurement to figure something out. Right, so here's an example. Let's say that we that'll represent the ground. And then we've got some object, could be a building, a house, whatever, away from us. And let's say that we're standing 200 feet away from that building. And we know the height of the building is 50 feet. And we want to figure out, if we have an object, we'll say on the ground, what angle would we have to tilt that at so it points at the top of the building. Now, obviously with an object with gravity, it changes a little bit. So let's assume we're shooting a laser pointer, which wouldn't really be affected by gravity. Okay, so the question would be, what is that angle right there? So the laser pointer is pointing at the top of the building. So essentially what we've done is we created a triangle. Created a triangle right there, where this is a 90-degree angle. So specifically, this is a right triangle. And now the goal would be to solve for that angle. Okay. Specifically, you would need to use what's called inverse trig, which we'll learn about later on. But that's an example of an application to a right triangle problem. There's also some problems that we can have that end up as not a right triangle. Let's say, for example, you had a boat in the ocean, and we had 2 observers on land that could see the boat. Let's say one here and one there. And maybe the boat, it's like at night, but the boat has a light on it. And they're trying to figure out where the boat is. Maybe if the boat needs help or whatever reason. There's 2 people trying to figure out the location of the boat. If 2 people can see the same object, and the object's not moving, if the object's moving, it gets a little more complicated. But as long as the object is stationary, and those 2 people can see that object, they can triangulate exactly where that object is. There's a couple things they need to know. One, they have to know how far apart they are from each other. That's, with GPS, that's pretty easy to figure out. So let's say that these people are 5 miles apart. Okay, like on a beach or something, 5 miles apart. Now, each person can see the boat from their perspective. So this person can look that way and see the boat. And they have to know the direction they're looking. Again, that's also very easy to figure out, either with a physical compass or an app that's a compass. You can just turn, look, and then look at your object and look down at your phone, and it'll tell you what direction you're looking. The problem is it won't tell you how far away something is. So I could say, I'm looking northeast, but if I see a light in the distance, I don't know if it's a mile, maybe it's 2 miles, maybe it's 1.5 miles. I can't tell. I don't know how far away it is. But this person can also see the light on the boat. And as long as we know these two angles, which we can get pretty easily, and we know the distance between the two people that are looking at the boat, we can triangulate exactly where the boat is. In this case, your triangle is right there. What makes that one a little bit harder is there's no right angle. So when we solve it, we can't use right triangle trig. We can use something else. Right, so there's a couple just kind of applications of trig. This second problem, it would be the exact same kind of diagram as, let's say that there was a fire in a forest and two people could see that fire. Maybe like 2 towers, or they have towers, like when you go hiking, you see those tall towers. If 2 people can see where the smoke is from the fire, they can triangulate exactly where the coordinates are of that fire. And then maybe you feed those coordinates into a computer and you send like a drone to drop water on it, or you tell a pilot where to fly to drop water. But you can figure out where the fire is. One person alone can't get the exact coordinates of the fire. They might be able to see smoke, but they don't know if it's 1 mile away, 1.2 miles, 2 miles, 3, 4 miles. You can't tell by yourself. Okay, so triangulation always needs a second point of reference, seeing the same thing you're looking at. So one nice thing about trig compared to the algebra is it's very, at least some of the applications are very relatable. Okay, they're not as abstract. All right. There's other applications, for example, like when you're building a house or framing a window or a door, that you can measure something and check to make sure that it's square. Like if you have a foundation for a house, you can take a couple measurements and measure a diagonal, and it'll tell you if your angle for your foundation is perfectly at 90 degrees. Because that's the way you build your house, that's what you want. All right, so there's lots of different applications to stuff that's more concrete. All right, any questions on those two? We're not really going to solve them today, just showing you some examples. Okay, so before we even get into talking about stuff like that, we've got to talk about something even more basic than a triangle, which is these 3 things that I just circled. What are those 3 things that I circled? Yeah.
Angles.
Angles. And that's what the first section is all about. Angles, how we measure them, how we classify them, and how we convert them. When I talk about convert, there's a couple ways you can measure angles. Well, there's several ways. In this class, we use 2 ways. I'm going to talk about those 2 ways today and how to convert between them. All right, so this is the start of trig. Okay, so first thing I'm going to do is define what an angle is. Well, when you talk about an angle, there's really 2 different things you could be referencing. Are you talking about an angle like that, all by itself? Or are you talking about an angle inside of a polygon? The definition is slightly different. I'm going to define the one that's on the left. So if you have an angle that's all by itself, that's where you take a ray take another ray and you put them together so they have a common start point. Okay, that is called the vertex, where those two rays meet. Now, when you draw something like a polygon, that doesn't have rays in it. What do we call the three sides in a polygon, like geometry-wise? They're not rays, they're not lines. They're
Line segments.
they're line segments. So in a polygon, where two line segments meet, that's an angle. Okay? But I'm defining an angle standing on its own. When you draw an angle, one of the sides is called the initial, and the other side is the terminal. In that case, the green one is the initial, and the black one is the terminal. And the way that you can figure out which side is which is when you draw an angle, if you go between the two rays, so let's say you have something like this and like that. If you go between them and you rotate counterclockwise, where you end is the terminal side. Where you start is the initial side. There's another example. So really, when you look at that, you have two angles. We have the angle inside, and then you also have an angle on the outside. We're talking about the angle inside. That's the one we're referencing. So if you rotate between the sides, the bottom one is the initial, and the one kind of on a 45-degree angle is the terminal. Now, if you rotate that, it doesn't change. So group all that together. Okay. The one that's pointing more vertical, that's still the initial side. And as you rotate counterclockwise, you would end at the terminal side. So any question on how to figure out which side is initial and terminal? Okay. When we don't know an angle in trig, we will often use a Greek letter to represent it. Some textbooks will use like lowercase letters for sides and capital letters for angles. I think that can get a little confusing for a couple reasons. First of all, sometimes a capital letter and a lowercase letter look the same. So like if you use the letter C and you write it down and there's no other letters around it, you don't know whether it's capital or lowercase. Also, when we start getting into looking at triangles and talking about the sides and angles, if I say, look at C, and we're using capital C's and lowercase c's, you don't know which one to look at. Right? So what we'll do to avoid that kind of confusion is whenever we're talking about an angle, it will be a Greek letter, and when we're talking about a side, we'll use an English letter. Now, we don't generally use all of those in the same problem, but we use, depending on how many we need, we might use up to 2 or 3 of them. Let's start with the first one. Does anybody know the name of that first one? Yeah? What is it? No, it's a Greek letter. It's a letter from the Greek alphabet. But I think I know what you mean. I think there is some kind of symbol. I can't.
It's in chemistry.
Yeah, there is a symbol, but that is a Greek letter. Anybody know what Greek letter it is? No? That Greek letter, that is alpha.
Oh.
These are all lowercase. There are capital versions, but these are the lowercase. How about the second one? Anybody have an idea?
Gamma.
There is a gamma up there,
Oh,
but it's not the
Oh,
second
that's
one.
beta symbols, man.
The second one is beta. The third one is gamma.
Oh.
How about the fourth one? Anybody know what that one is? Yep,
Is that theta?
that's theta. And how about the last one? Anybody know what that one is? The capital version of it looks like this. Well, it looks kind of like a horseshoe. If you take physics, it's the symbol for resistance. But yeah, that's omega. We don't use the capital. We use the lowercase. I would say the most common one that you use is theta when you're just talking about a single angle that you don't know. It's kind of like using x in algebra. We use x almost all the time for a variable. We use theta a lot. If we need to represent more than one angle, let's say we're talking about a triangle and we don't know any of the angles. Well, now we need 3 Greek letters. Generally, the 3 that we use are alpha, beta, and gamma. Hey, there's no real rule when you have to use which one, just like in algebra. There's no rule you have to use x as the variable. But generally, we'll use a Greek letter. But you can pick whichever one you want. Questions on those? Okay. So if I asked you to sketch a 90-degree angle, okay, some people might do it like that. That's a 90-degree angle. Other people might draw something like that. Is that still a 90-degree angle? Yeah, even though I rotated it, it's still 90. Well, if we want everybody to sketch the same way, okay, and have it be oriented the same way, then what we can do is define something called standard position. Standard position is when you draw an angle, and it has to have 2 things. 1, the vertex of the angle is at the origin. 2, the initial side is on the positive x-axis. So if we look at that angle by doing that to it, is that angle in red still in standard position? No, Kelsey, what's wrong with it?
The vertex isn't at the origin.
Yeah, the vertex is not at the origin. Okay, so now it's back in standard position. How about if I did this? And then put it like that. Okay, is that standard position? No, yeah, why not?
Because it's not on the positive x-axis.
What is not on the positive x-axis?
The initial side.
Yeah, the initial side. The vertex is at the origin, but the initial side is not on the positive x-axis. Okay. So now, if I asked you to sketch a 90-degree angle, and I said to do it in standard position, everybody's 90-degree angle would have the same orientation. So it just gives us a way to draw things in a uniform way. So any questions on what it means to sketch or draw an angle in standard position? Okay. So one way that we can measure an angle is in degrees. We're going to talk about a second way in a little bit. Now, we use angles, or we use degrees as one way to measure them. But we can look at angles in a couple different contexts. Let me show you what I mean. Okay, so one way we can measure angles is in a shape, right? So we can look at a triangle and measure the angles inside of a shape. Another use for angles is to talk about an amount of rotation on a circle. Still talking about an angle, but it's just a little bit different context. So as I start to rotate this angle in a counterclockwise direction, it shows me a number in the lower right. That number is the angle between the initial side and the terminal side. This only lets me draw angles in standard position. I can't move I can't slide the angle, and I can't move the initial side. I can only move the terminal side. Now, that's about halfway through quadrant 1. if I were to make a full rotation in the direction that I'm going, counterclockwise, how many degrees would that be in a full rotation? No one?
360.
It'd be 360. How about like a half rotation? Yep.
Maybe.
Yep, that would be 180. And how about if we did a quarter of a rotation, or a quarter of a revolution? Yep,
9 degrees.
that would be 90. So different angles tend to come up more than others, depending on what you're talking about. 30s, multiples of 30 and 45 come up a lot. Those are very common angles we work with in trig. Whether it be an angle in a triangle or an amount of rotation on a circle, which technically corresponds to a triangle. So we're going to make lots of connections between like a rotation amount on a circle and a triangle. Now, I mentioned here clockwise, counterclockwise, counterclockwise, counterclockwise. What's the other direction you could go besides counterclockwise? Yeah,
Clockwise?
you could go clockwise. And anyone have a guess, if you go clockwise, what kind of angle do you think you're going to get? You saw what happens when we go counterclockwise. How about clockwise? Yep.
We get a negative.
Yeah, you get a negative. Now, negative angles, they don't make sense when we're talking about shapes. You'd always have positive angles. But when you're talking about a circle, the negative indicates a direction of rotation. That's all that the negative is. So negative means you are rotating in a clockwise direction. And that's pretty much it. Okay. So any questions on that idea? Any questions on this box on the lower right? No? Yeah.
I'm guessing that's something that may involve distance?
What might involve
Or
distance?
it's some sort of measurement, I know that.
Okay, what's the top number you think?
The top number is it's the degree.
Is the degrees, yes. Anybody know the bottom number? 0.35? Okay, so that's what we need to talk about eventually. Okay, so that bottom number is something important, very important. Much more important than the degree number. Yeah.
Is that the distance it's gone around the circumference?
In this particular, well, I don't have any grid lines. I don't know what these grid lines represent. If each one of these grid lines is really one unit, 1, 2, 3, 4, then no, that is not the amount of distance that it would have covered on the circle. If each one of these grid lines was a quarter, half, 3/4, and that ended right on a 1, then the radius of this circle would be a 1, and then I would have a little bit different answer to your question, which we're also going to talk about. All right, so we'll talk more about that bottom number. Okay, so I already said that. Angles measured in a counterclockwise direction are positive. Angles measured in a clockwise direction are negative. I know we'll diagram in case you're not sure which way is which. And what will happen to my angle if I go around more than one rotation? Let's say counterclockwise. What kind of number do you think I'll get for my angle if I go around more than once? Yeah.
Would it be larger than 360?
Yeah, it will be larger than 360. So going around more than once just indicates, it means you have an angle larger than 360. And that's indicated by like this spiral. Because if you didn't have this over here, you wouldn't know the difference between that and that. They look the same. But the spiral kind of shows you went around more than once. Now, in a triangle, this isn't true. You cannot have an angle larger than 360. In fact, what's the largest an angle can be in a triangle? Yeah. Yeah, up to 180, not including 180. But when you're talking about other polygons, you definitely can have angles bigger than 180. Depends how many sides you're, like if you're thinking of like a regular polygon, the more and more sides you add, the more the sum of the interior angles increases. So like in an octagon, I think there's, well, 8 angles. And I think each angle is, I think it's 135. Each angle in an octagon is 135. Okay. So the more sides you put in your polygon, the larger the angles start to get. But in a triangle, you definitely cannot have a 360-degree angle, at least in a flat, like Cartesian triangle. There are other kinds of triangles. We don't study that though. Okay, all the trig that we do, it's basically on a coordinate plane, meaning it's flat. Compared to like if you connected like 3 points on the surface of the Earth, that's a triangle. But if you connect like really far away points, like North Pole, Boston, London, it's a spherical triangle. So it's a triangle that's curved on the surface of the Earth. Those kind of triangles are very different. Okay. So what we study is Cartesian stuff. All right. Next thing we're going to look at is what does it mean if angles are coterminal? Coterminal, think of what the word co means. Co usually means like together or with. Like co-captains, like they work together, they're both kind of helping out. So co usually applies to 2 things. If 2 angles are coterminal, then that means they have the same initial and terminal sides. So if 2 angles are coterminal, they have the same initial and the same terminal sides. Here's a picture of 2 angles that are coterminal. 90, 450. In each of those pictures, the initial and the terminal side is in exactly the same spot. Here's another one. Maybe 810. That's another angle that's coterminal with the first 2. Does anybody see a pattern? How I could get from 90 to 450 or 450 to 810. I don't want to keep using this picture. Say I wanted to just start listing them on paper. Yeah?
Add 360.
Yeah, you can add 360, and that'll always give you another angle that is coterminal with what you started with. Besides adding 360, what else do you think you could do? Yeah?
Subtract 360.
Yeah, you can subtract 360. Okay, so I didn't get it perfect, but negative 270. And the idea of working with coterminal angles is that when we're doing trig, we try to work with the simplest angle that we can. So if I go on the calculator and type in something like sine of 370, you don't have to worry about what that means right now. Just watch what I'm doing. I get an answer of 0.1736. Well, there is a simpler angle that I could work with, a smaller angle, that for the purposes of doing trig will give the exact same result. Any angle that's coterminal with 370, I could use in that problem. What is an angle that is coterminal with 370 and smaller? Yep. Aiden? 10. So are 370 and 10 the same number? No, that's not what I'm saying. I'm saying the angles are coterminal, which means when you plug them in as an argument to a trig function, you will get exactly the same answer. Yeah. Yeah. So generally, we try to avoid angles that are too big. We don't want to work with an angle in the thousands. We can subtract 360 to make it smaller and then work with that. We also don't want to work with angles that are negative. So if I had an angle that was negative, I would add 360. I always try to work with an angle between 0 and 360. All right, so let's see if we can find some angles that are coterminal with one that I give you. Okay, does everybody have the adding and subtracting 360 to get a coterminal angle? Okay. So the sketch, again, it doesn't have to be perfect. We're just going to do a quick sketch of an angle and then find an angle that's coterminal and positive and one that's negative. So let's start with 30 degrees. They want it sketched in standard position. So what does that mean about the vertex? Yeah,
Is that the origin?
no choice about that. Vertex is the origin. And what about the initial side? Yeah,
It's on the positive x-axis.
yep, initial side has to go right there. Now they want an angle of 30 degrees. Think about quadrant 1. How many degrees are in the whole quadrant?
90.
90. So this is the third of that. So you want to draw an angle, think of a half, and then try to go a little bit less. That's probably about 30 degrees. Okay, what would be an angle that is coterminal with 30 and positive? Yeah,
390.
390. And an angle that's coterminal with 30 and negative? Yep, Nolan?
Negative 330.
Good. That's it. So there's an angle that's coterminal and positive or negative. I think the original angle was fine. I would have worked with that, but they wanted us to find those two. Any question on that one? Okay. Let's try 145. So again, standard position. Start with that. And what quadrant is 145? Where is the terminal side going to end up in? Think you see yet? Yep, it's going to end up in the second quadrant. Is it going to be closer to the y, closer to the x, or right in the middle? Yeah.
In the middle.
So right in the middle, so if this is 90 and this is 180, if you add those up and divide by 2, that gives you what's right in the middle. And that's 270 divided by 2, which is 135. So 135 would be right in the middle. So this one, yeah,
It's going to be closer to the
a
x-axis.
little bit closer to the x-axis, just 10 degrees closer. All right, so if you think of halfway, just try to draw it a little bit less. Okay, so there's my sketch. Now, what would be an angle that is coterminal and positive? Yeah,
505.
505. And how would I find an angle that is coterminal and negative? Yeah.
Subtract 360.
Yeah, so if it's tough to do, just take 145 minus 360, and you get negative 215. Okay, so there's 145. And how about this one? Negative 45. Sorry, I'll fix that. Okay. So again, start with your initial. Can't change that. Where's negative 45? It's going to put the terminal side where?
That's in the fourth quadrant.
That's going to be in the fourth quadrant. Closer to X, closer to Y, right in the middle. Which one? Right in the middle. Anything that's a multiple of 45, when you sketch it, you can think of that as having like a slope of 1 or negative 1. Okay? 45s are always right in the middle. So the best you can, put it in the middle. And now what would be an angle that is positive and coterminal? Yeah.
315.
315. And an angle that is coterminal and negative.
Negative 405.
405, yeah. Okay, so finding coterminal angles, not really a hard thing, but important to be able to take an angle and simplify it to something that's easier to work with. Questions on that? Okay. So now we're going to look at 3 definitions that can be used to classify angles based solely on how large they are. Start with this one. What would make something an acute angle? It actually has to meet 2 criteria. Yep. Less than 90. What else? I can think of something less than 90 that's not acute. Yep.
More than 0.
It's got to be more than 0. Yep. Now, in a polygon, would you ever have an angle less than 0? No. But when you're rotating on a circle, you can. So in the context of an angle, it has to be between 0 and 90. The next type of angle, let's try this one different, is exactly 90. What's the name if it's exactly 90? Yeah?
Right.
Yeah, that's a right angle. Okay, that's when your angle is exactly 90 degrees. Right? How about this one? An angle that is obtuse. It also has to meet 2 criteria, kind of like acute. But what's the measurement an angle could be and be in the obtuse range? Yeah?
Between 90 and 180.
Right, between 90 and 180. Open interval, not including either one. If it's exactly 180, we call that a straight angle. In triangles, we never have that situation come up, but you could have any of those in a triangle. All right, so the next definition is going to apply to a pair of angles, okay, 2 of them together. What would make 2 angles complementary? Yep.
I think that's the one that adds up to 90.
Okay, they have to add up to 90, and there's another part to it as well. Because again, I can think of 2 numbers that add to 90, and they're not complementary. Yep.
They have to be next to
No, I don't think they have to be next to each other. They can be, physically, they could be drawn separate. That's okay. Yeah. Yep. Okay.
That can't be 90 and 0.
Yeah, well, they can't. They can be 90. A 90 and a 90 together is fine, like an L, back to back. You can have 2 L's together, and that. Oh no, that would be supplementary. Never mind. You're right. They can't be 90 and they can't be 0. So they have to add up to 90 and they have to be positive. So I didn't say they can't be 90 because by me saying they have to be positive angles that add up to 90, that would automatically exclude using 90 and 0 because 0 is not positive. Yeah. All right. Now, what do we call 2 angles that add up to 180? Yeah.
Supplementary.
That's supplementary. And again, they also have to be positive. So for example, 200 degrees and negative 20. Yes, they add to 180, but they are not supplementary. Okay? Negative angles do not have complements or supplements. The complement is what would make the angle add up to 90. The supplement is what would make it add to 180. All right. So let's try a few, just finding some complements and supplements. And then we'll finish up with the last thing, which is another way to measure angles. Let's try it. So find the complement and the supplement of 48 degrees. Okay, let's start with the complement. What would be the complement of 48 degrees? Charles?
42 degrees.
42, perfect. And the supplement of 42? No? 132, perfect. Now, once we start working with radians, you're going to want to be able to do the same thing in radians too. It's better to become familiar with radians than to try to avoid radians, because it's going to be very cumbersome if you're not comfortable working in radians. Technically, could you always take something that's in radians, change it to degrees, do all the work in degrees, and then change it all back again at the end? You can. There's a lot of extra conversions in there. You're not going to have enough time to do that, and that's introducing too many extra steps. So you want to be comfortable when we start working with radians. It takes a while to get comfortable, but you will, just like we did there.
Did you do the supplement of 48 or 42?
The supplement of, well, let's double check it. Let's take 48 and 132 and add them up. If they add up to 180, then we did it right. Yep. All right, let's do the complement and the supplement of negative 18 degrees. Okay. What is the complement? Yeah.
Can't have one as negative.
Yeah, it doesn't apply. There's no complement, there's no supplement. Don't have them. All right, how about x degrees? I do have to tell you though, assume that x is acute. If you didn't know that, then maybe it wouldn't have a complement. Like if x was 100 degrees, there wouldn't be a complement. But now you know it does have a complement. How would you get the complement of x degrees? Yep.
90 minus x.
Yep. So the complement is 90 minus x, and you're guaranteed x is not bigger than 90, so you will not get a negative. That's good. And what about the supplement? Yeah. 180 minus x. And whatever that comes out to, we put a degree symbol on it. Okay. Any questions on complements or supplements? Okay. So the last thing we're going to look at are what are called radians. If you take calculus next year, everything you do related to angles will be in radians. Degrees is not really used in higher math. Right? I think they use degrees in like simpler, like lower level kinds of math because it's easy to understand, but radians makes things a lot simpler in calculus. So it's just another way to measure an angle. So I'm going to first try to describe a little bit about what a radian looks like, and then I'll get into how you convert between radians and degrees. Okay, I'm going to start with that picture. What I've drawn in that picture, it's called a central angle. A central angle is just an angle drawn inside of a circle, and the vertex of the angle is the center of the circle. That's angle ACB, or BCA, either way. When you draw an angle inside of a circle, the initial side and the terminal side will hit the perimeter, the circumference, at some point. If you connect, following the path of the circle, between the 2 points that I just marked, that is called an arc. Okay, so now, if this angle right there is a certain size, then it will cause something very special to happen between the length of that arc and the length of that radius. And that special number that the angle would have to be is 1 radian. Anybody have a guess what would happen? This picture is almost to scale. I think I'd have to tilt in the terminal side a little bit. But if that angle is 1 radian, does anybody have a guess what the connection is between the length of that arc and the length of that radius right there? Yeah?
Would they be the same?
Yeah, they would be the same. Yeah. So if the length of the arc is equal to the length of the radius, then that angle is exactly 1 radian. And you can read that sentence either way. If you have an angle that's 1 radian, then the lengths match. Or if the lengths match, then you have an angle that's 1 radian. Now, that doesn't really do anything to help us to convert between degrees and radians, but it at least gives you kind of a picture you can imagine in your head for what a radian would look like. If this angle is not 1 radian, then this arc will not match the length of the radius. So any question on that special property? Okay, that's important because we're gonna come back to that at some point, and we're going to have to know a connection between the length of the arc and the length of the radius, and that is going to help us with that connection. If it's 1 radian, we know they're the same. And that'll give us a starting point for doing something. Any questions? Okay. So now, how do we convert between radians and degrees? Now, earlier, when I brought up this picture, and I just don't remember where I had it exactly, somewhere around there, I asked about this bottom number. And one thought somebody had was maybe this bottom number is measuring how much of the circumference we've traveled. And I said, well, I'm not sure about the units on my grid lines. Okay? If each one of these grid lines is 1 unit, so 1, 2, 3, 4, if that's a circle with radius of 4, then no, this number is not how much of the circle I've traced. But if each one of these grid lines is a quarter of a unit, quarter, half, 3/4, and let's say the circle ended right on the 1, looks like it's a little bit off. Say it did end on the 1. Then this number, the bottom number, would have something to do not only with the size of this angle, but with the amount of distance I've traveled on the perimeter as well. So let's look at that connection. So we're going to look at a connection in a very special circle. This circle we're going to look at is called a unit circle. A unit circle means a circle with a radius of 1 or diameter of 2. Usually we say radius of 1. And in a unit circle, something very special happens that I'm going to show you. Okay. Yep, sign up. So now, let's say I have this circle, right, and I draw the terminal side right here. Let's say I measure this angle right here, and it comes out to, I'm just going to make up a number, 0.7 radians. Let's say this comes out to 0.7 radians, a little less than 1. If this is a unit circle, if that's 0.7 radians, then that would be 0.7 feet, whatever units we were using. The important thing is these two numbers will always match. 0.7 radians, 0.7 feet. 1.2 radians, 1.2 feet. 5.4 radians, 5.4 feet. The two numbers will always match on a unit circle. We're not going to prove that. We're just going to write that down. Now, it doesn't work if you measure it in degrees. That doesn't work. So if this comes out to 30 degrees, that would not be 30 feet. No, it only works if you measure in radians. So if you measure the angle in radians, it comes out the same as the length of the arc. But it has to be a unit circle. Okay, so just saying that again, if you measure an angle in a unit circle, the angle is equal to the arc. Angle equals arc. What happens on a non-unit circle? Well, not that. The angle is not equal to the arc. So the fact that this special thing happens can help us to figure out how many radians it takes to go all the way around the circle. Okay, we already know this. Let's write down 1 revolution is how many degrees? Yep. 360. We already know that. The question I want to know is how many radians is 360? Once I fill in that box, then I can convert between radians and degrees all day. Okay, to convert between two things, all you have to have is like a point of reference. You need to know one thing. For example, if I tell you 24 feet equals, 24 inches equals 2 feet. If I give you that fact, or any other true fact about feet and inches, you can convert between feet and inches all you want. You just need to start with something you know is true. 1 foot equals 12 inches would be even simpler, but there's nothing wrong with that either. 2 feet equals 24 inches. Okay, it's kind of like your point of reference for figuring out other things. Okay, so now let's look at this. In a unit circle, the measure of the angle is equal to the length of the arc. So now, let's say we have a circle like that. If I put the initial side here, and I put the terminal side there, that would be my arc. How much of the circle is that arc? Yep.
Quarter of it.
Right, so a quarter circle corresponds to a 90-degree arc. How about if I put my terminal side there? How big of an angle have I just created? Yep. 180. And how much of the arc does, or how much of the arc does it take up now in terms of the circle? It takes up half. Okay. So now let's put my terminal side here. How big is that angle? About Colin? 270. And how much of the circle does that arc take up? 3/4. So now, let's go all the way with it. We put our initial side here, put the terminal side here. Draw your arc. How big is that angle when the initial side and the terminal side are right on top of each other? Yeah?
360.
That's 360. And now I have an arc that's so big, it takes up the entire circle. But remember, if I can figure out the length of that arc, then I will know the measure of the angle in radians that goes all the way around the circle. So I just have to be able to figure out the length of this arc. And it's exactly the same as the size of the angle. Now, that arc is so big, it takes up the whole circle. Not a quarter, not half, not 3/4, it's the whole thing. What do we call an arc that takes up the entire circle? Yeah?
Circumference?
It's the circumference. So what we've basically reduced this problem down to is if we can find the length of the circumference, that will tell us how big the angle is in radians that goes all the way around the circle, because they're the same. So let's see if we can find the circumference. What's the formula for circumference? So it does have pi in it. Pi r squared is area. Still a good formula. We're going to use that in the future, but just not today. Yeah,
2 pi r.
2 pi r. And specifically, we are dealing with a unit circle. What is the radius in a circle that's a unit circle? 1. So let's plug in 1 for my radius. And if I simplify that but leave the answer in terms of pi, what do you get for the circumference of the unit circle? Yep,
2 pi.
2 pi. So now we know the length of the arc that goes all the way around the circle. So how many radians would be the angle that goes all the way around the circle? Think they know? We know the length of the arc, and look at what it says the length of the arc is equal to. It's equal to the measure of the angle. And it's automatically going to be in radians. Yeah? 8?
360?
That's degrees, but our answer needs to be in radians. Yeah?
2 pi.
2 pi. Yeah. The length of the arc is equal to the measure of the angle. The arc goes all the way around the circle, and it's 2 pi. So the angle that goes all the way around the circle is also 2 pi. That's why, if you noticed when we did this, and I went all the way around the circle and stopped at 360, it said 2 pi. Yeah. All right, so now we know right here is 2 pi. One thing you'll notice, though, is you do not put radians. Okay? When you're labeling an angle that's in radians, if you leave the degree symbol off, it's assumed your answer is radians. Okay, you'll never see RAD. Now, okay, so that's what I just wrote down. 1 revolution equals 2 pi. So we got that. But how can I simplify this a little bit? It's kind of like saying in 4 feet, 4 feet is 48 inches. You could give me something a little simpler than that. Yep.
180 equals pi.
Right, we could just say that 180 degrees equals pi radians. And we could go even simpler than that. Usually when you give somebody a conversion, you put a 1 in it. Like you say, in 1 hour, there's 60 minutes. In 1 day, 24 hours. You don't normally say in 2 days, there's 48. If you're trying to give someone a conversion, you give them the simplest one you can. So let's say I want to take that. I put radians just so you could see it this time, but I want to get used to not writing it. Let's get a 1 on the right side. How could you turn the right side into a 1 here? Yeah.
Divide both sides by 180.
Divide both sides by 180. Now that says pi over 180 radians, RAD is invisible, equals 1 degree. Now you have a formula for 1 degree. If I wanted a formula for 2 degrees, what could I do with the equation I have right here to convert it into something that would give me a formula for 2 degrees? Peyton?
Did you just multiply both sides by 2?
I could just multiply both sides by 2. Now I have a formula for 2 degrees. What if I wanted a formula for 6 degrees? What could I do? Yeah, multiply by 6. The number you're putting in the red box, that's not what's important. What's important is right here. If you want to take and convert something from a certain amount of degrees into a certain amount of radians, you take whatever number you're trying to convert and you multiply by pi, and you divide by 180. Those are the two steps to change something from degrees into radians. You multiply by pi, and you divide by 180. Now, let's look at that same equation again. Pi radians. Actually, again, I want you to get used to not seeing R80. How could I get a 1 on the left side? Yep. Divide by pi. And what do you think this is going to give me a formula for? Yep.
Converting from radians to degrees.
Right. This is going to give me a formula that converts the other way. I do need to put the circle on 180 because that's the degree. Okay. I don't need to put a label on the 1 because that's the radian. So now, if I wanted a formula for 5 radians, do a times 5 and a times 5. Now you have 5 radians equals, and you have a calculation you could do it. 180 times 5 divided by pi. Okay, the important part is not what's in the black box. It's what's right there. It's multiplying by 180 and dividing. The pi is in the bottom. Okay, so we do have to remember which one is which. They are kind of easy to mix up because they're very similar. But the way that I can try to help you to remember it is the following. When I say degrees, I want you to think 180. Okay? When you see the number 180, think degrees. When you see a pi, think radians. Okay, so just remember those two things. 180, think degrees. Pi, think radians. If you can remember that, then all these steps become automatic. You don't have to remember the order. So let's try changing degrees to radians. So we're going to multiply 30 degrees by something. It's either pi over 180 or 180 over pi. Think about the units you want to end up with. You want radians in the final answer. So that means you want which unit to cancel out as we do the problem. Yeah?
Degrees.
We want degrees to disappear. Right now, you can think of degrees as being in the top of a fraction. You can put it over 1 if you want. Where would degrees have to go in the second fraction to cancel out the first fraction? Yeah?
The denominator.
We go in the denominator. Now, when you think degrees, what's the number I said to always think of? Yeah? 180. So the 180 goes with the degrees. Radians is in the top. What's the number we always think of when we think radians? Yep. Pi. Now, degrees cancels out. You get 30 pi over 180. We need to reduce that as much as we can. What number goes into both 30 and 180? Yep. 30. And that would leave you with pi over, how many times does 30 go into 180? 6. So 30 degrees is pi over 6 radians. And I can show that to you by going like that. So you'll notice some answers have a pi, some have a decimal. Generally, anything that's a multiple of 30 or 45 will be written as a fraction with pi. A non-special angle, like something that's not a multiple of 30 or 45, we'd have a decimal. Let's try another one. Okay, converting degrees to radians. What unit is going to go in the bottom? Because we need it to cancel. Yeah. Degrees. Radians is in the top. What number do we always put with the degree symbol? Yeah.
180.
180. And what number always goes with the radian label? Yeah. Hi. I usually cancel before I multiply, then I don't have to write it twice. What number goes into both? If you don't find the biggest number, you'll just have to do it more than once, but ideally I'd like the biggest number. Yep.
4.
So 4 only goes into even numbers. 44 wouldn't go into 45 evenly. Yep.
9.
9. Yes, I agree. 9 does go into both. I can think of something bigger though. 15 goes into both, but again, I can think of something bigger. Yeah?
45.
45. Okay, so 45 goes into itself once. And how many times does 45? Did you say 45 or did you say 4?
I said 45.
Oh, I thought you said 4.
No.
Oh, I'm sorry.
That's okay.
Yeah. I just thought of that after. How many times does 45 go into 180? 4. So now, when we reduce that, you get 1 pi. Just write pi over 4. Now, this one, once you start to learn sum, you can kind of take a shortcut. We already know 30 is pi over 6. How does 60 compare to 30? Yep,
It's double.
it's double. So just double pi over 6, which would reduce to what? Yeah,
Pi over 3.
pi over 3. Now, at first, you might not know that, so you have to go through all the steps, multiply by pi, divide by 180. But as you start to learn the basic ones, then if somebody asked me to do like 240, I would just say, oh yeah, 240 is 60 times 4, 4 pi over 3. Quick way to convert it in my head. But again, it takes a little while to learn some of these. If they wanted a decimal, let's just practice one of those. How do you think I would round that to a decimal? Pi over 3. Tell me the buttons I would press on the calculator. Yeah?
3.14.
No, not. I don't want to use 3.14. Yeah?
You would use second and then the arrow to
Yeah. So when converting something to a decimal, if you want to use like 20 decimal places for pi, that's okay. You can do it that way. Or press the pi button, okay? Because the pi button is more accurate. So it's about 1.05. If you use 3.14, it's going to mess up our accuracy. And if we use that to then do something else, it messes that up later on.
What would be pi button?
The pi button is okay because it's more accurate. Yeah.
Where is it?
Oh, it's above the exponent. You have to press second and then the exponent.
Oh.
Okay. So let's try 2 going the other way. What would I multiply by to get the radians to cancel out and be left with degrees now? How would we convert 2 degrees? Yeah.
180 over 5.
Right. The 180, think of the word radian is next to pi. So we have radians in the top. We need to put radians in the bottom to cancel out. Pi's cancel out. And how many times does 2 go into 180? Yeah,
90.
90. So 3 pi over 2 is 3 times 90 degrees, or 270. And let's finish up with this one. 180 in the top, pi in the bottom. What's going to cancel out completely there? Yep,
And
pi. And how many times does 3 go into 180? Yeah, 6. D. 60. And then I'm left with 2 times 60, which is 120. And you do need that degree symbol. If you don't put the degree symbol, that's 120 radians. That's not what we want. Okay, so homework is the take home. It's due, let's see, Wednesday, 8 a.m. Eastern Time on the 27th. If it's late, it would be a 0. It's going to close right at 8 a.m. You will have 90 minutes. Doesn't have to be consecutive. You can work on it in different chunks, but close it out if you're not working on it, because if you just leave it running in the background on your computer, the timer will count down. Is anybody not going to take the test because they might not have reliable internet or can't get it done tonight? So everybody's taking it? Okay. Any questions about, it's going to be on Edge Elastic and it's going to open at 2:40 p.m. today. You will have access to the graphing calculator if you need it on the Chromebook. Yeah. It's going to be on pair assessment, but you also will not need a password. Yep.
Thank you.